This video is about areas and volumes of similar solids. So when you're looking at two similar solids, first you can find what's called the similarity ratio, which just compares the lengths of the different sides. So let's say we're working with two triangular prisms. So here's our first one. And our second one. So if we were to just compare the lengths of the sides of these two prisms, that would be called the similarity ratio. So if I was to take a look at this left side, the 4 inches, and compare it to the corresponding side on the other shape. So the corresponding side is the one in the same spot. Since these have the same orientation, it's easy to tell, hey, that left side, that's going to be 12. So we're comparing 4 to 12. And you can do that two ways. You can write it with this colon in between, or you can write it as a fraction. Those are both the proper way to write this similarity ratio. Both of these can also be reduced. We need to find the biggest number that would divide into both a 4 and into a 12. So 2 does divide into both of them, but we need the biggest. So we would use 4 itself. 4 divided by 4 is 1. 12 divided by 4 is 3. 4 divided by 4 is 1. 12 divided by 4 is 3. So 1, 2, 3. 2 as in T-O, that's usually how we say that, colon, 1, 2, 3. Or 1, 2, 3. So we're comparing the lengths of the sides. For the two shapes to be similar, every single one we compare would have to match. They'd all have to reduce to that ratio of 1 to 3. So for example, if we were to check the bottom, 3 to 9, and reduce, they both divide by 3, we come up with the same ratio, 1 to 3. Or if we were to do this length, 12 to 36, both divide by 12, and again it becomes 1 to 3. So every similarity ratio matches up. If we did the last one, 5 to 15, it would also match. So these two shapes are definitely similar. Now things can become a little more complex if we were to look at the area and volume ratios along with those similarity ratios. So let's look at a rectangular prism. Two rectangular prisms so that we can talk about these similarities. If we were to check, all these side ratios would match up. These are definitely similar. Let's find the area and the volume ratios. So area of a prism, surface area, is all these outside. If I were to look at the outside rectangles and find the area of every outside rectangle, those areas all added together would be the surface area. So you could do each rectangle individually, find the area, add it together. Usually we go with the shortcut, which is to find the perimeter of the base times the length of the prism plus 2 times the area of the base. So the base of the prism is 4 of these sides will have that same length, so 18 goes with 4 of these sides. The base is the top and bottom areas that don't have that length, so they don't have the 4 similar sides going with them. So the surface area of this larger prism, we would do perimeter of the base. We would have 12 on both sides, 10 on both sides. So perimeter would be 12 plus 10 plus 12 plus 10, which would be 44, times the length, which is 18, plus 2 times the area of the base. The area of this base would just be length times width, so 12 times 10. Plugging that all in, you end up getting 1032. Surface area of the smaller figure. Perimeter again, 6 plus 5 plus 6 plus 5. That gives us 22 times the length. That gives us 9 plus 2 times area of the base. 6 times 5 gives us the area for 30. So altogether, the surface area is 258. So if we were to compare one to the other, 258 to 132, or 1032, I can reduce these. Both of these actually divide by 258. It gives me a surface area ratio of 1 to 4. So we want to compare this to the volume ratio and to the regular similarity ratio, or the side ratios. So if we were to do the side ratios, just take these amounts, 6 to 12, and reduce. Both these divide by 6, we get 1 to 2. And if we were to do the volume of a prism is, of a rectangular prism, is length times width times height. So 18 times 10 times 12, which is 2,160. Volume of the smaller one, length times width times height again, 9 times 5 times 6 is 270. Again, putting these together, 270 compared to 2,160. They both divide by 270. So this reduces to be 1 to 8. So the 3 we had was the similarity ratio, which is 1 to 2. The surface area ratio, which is 1 to 4. And the volume ratio, which is 1 to 8. Now, when we work with these, we don't want to have to find the entire surface area every time, the entire volume every time. We want to be able to kind of come up with a shortcut. So the shortcut is that the surface area ratio is the similarity ratio squared. If I do 1 squared and 2 squared, I get 1 to 4. So similarity ratio, or surface area ratio, is similarity ratio squared. The volume ratio, again, has a shortcut where we compare it to the similarity ratio, and it is the similarity ratio cubed. Cubed means multiply it by itself 3 times, so 2 to the third is 2 times 2 times 2, which is 8. So we can always find the surface area ratio and the volume ratio using that similarity ratio. So we can go back and forth. Now I can't go straight from surface area to volume, but I could go from surface area back to similarity, then to volume. Or I could take, if I knew volume first, I could go from volume back to similarity, then to surface area, because both of these are related to the similarity ratio. So let's look at an example where we were only given one of them and we want to find the other ones. So let's say we have a surface area ratio of 18 to 50. So first, any ratio they give us, we want to see if they reduce first. Reducing is always the first step. It can make everything a lot easier. So what divides into both 18 and into 50? Well, the biggest number that divides into both of those is 2. That leaves us with 9 compared to 25. So we know that the surface area ratio is that similarity ratio squared. So we need to do the opposite, because now we're going backwards. We're not starting with similarity, we're starting with surface area. Which means the opposite we're going to have to do is we need to square root these numbers. So square root of 9 would be 3, square root of 25 would be 5. This is now the similarity ratio. We brought it back down to that similarity ratio because now we could use the similarity ratio to find volume. We know the shortcut to get from similarity to volume is to raise it to the third, or to cube it. So 3 cubed to 5 cubed would give us 27 to 125. And that would be our volume ratio. So for given volume, we can do this same idea. For given a volume ratio, we can find similarity and surface area. So same first step, reduce. Both of these divide by 8. 2 would have worked, 4 would have worked. We want the biggest, which is 8. If you do use a smaller one, let's say I didn't know there was a bigger one and I start with 2. 64 divided by 2 is 32. That just means we'd have to do it again. Well, both of these divide by 2 again. Nope, that's still not reduced. I can divide both of those by 2 again. So you can do it in multiple steps. It just goes quicker if you can figure out the biggest number that goes into all of them first. Now this time it's a volume ratio, so instead of square rooting, we need to take the cube root. The cube root of 1 and the cube root of 8. The cube root is asking what number multiplied by itself 3 times is this inside number. So 1 times 1 times 1 is 1. That means the cube root of 1 is 1. 2 times 2 is 8. 2 times 2 times 2 is 8. So cube root of 8 is 2. This is our similarity ratio. If that's all they wanted, then we could stop here. They could also call it the ratio of the sides, or they could also refer to it as ratio of the perimeters. Since perimeters is just adding everything together, it's the same ratio as the sides. To get it then to a surface area ratio, we would raise it to the second power, or square it. So 1 squared to 2 squared gives me 1 to 4, which is our answer. So this is now a surface area ratio, which means we don't actually need a fourth step because that's just our answer. So we can also use this to find a volume or surface area we don't currently know. So let's say we have 2 similar figures. And we know their surface area. We can use SA for surface area. Let's say we know the volume of just one of the figures. That's 200 meters cubed. What is the volume of the larger? So to do this, we're going to be setting up a proportion, which is two fractions equal to each other. When we do these fractions, we need our ratios to be the same. Since we're looking for volume, we need these to be volume ratios instead of surface area ratios. So first we're going to change these from surface area ratios to volume. So we have to reduce first. Both of these divide by 2. This is surface area currently, so we have to square root. And then to get it to volume, we have to raise it to the third power. 6 to the third is 216, 5 to the third is 125. Now this ratio I can use to set up my proportion. That's the first fraction, 216 over 125. Then it says the volume of the smaller figure is 200. So looking at our ratio, 216 is bigger than 125, so the smaller figure would go with the 125. The 200 has to go on the bottom because the smaller number over here was on the bottom. And we want to find the larger figure, so we use an X for what we want to find. Now we can cross multiply. 200 times 216 is 43,200. 125 times X is 125X. Divide both sides by 125. And the volume of the larger figure is 345.6 meters cubed. That's right, meters. There. You can do this and set up a proportion if they give you volume first and you want to find surface area. Let's say we have two similar figures. And they have a volume 125 centimeters cubed and 143 centimeters cubed. The surface area of the smaller figure is 175 centimeters squared. What is the surface area of the larger figure? Okay, so we need to take our volume ratios and change them to surface area ratios. We try to reduce, there's nothing that divides into both of these. So we skip reducing and go on to taking the cube root. Since it was volume instead of surface area, we take the cube root. To make 125, you would do 5 times 5 times 5, so cube root of 125 is 5. To make 343, you do 7 times 7 times 7, so cube root of 343 is 7. So that's the similarity ratio, or the side ratios. But we need surface area, so we square each of those, 25 to 49. So that would be the first part of our fraction. It gives us the surface area of the smaller figure is 175. So that's what we put on the top. Since 25 is smaller than 49, smaller figure top, larger figure bottom, smaller figure top, larger figure that we're looking for on the bottom. And then we multiply. 25 times x is 25x. So then we do 49 times 175, which is 8575, so 8,575. And then we divide both sides by 25. So the correct surface area of the larger figure is 343 centimeters squared. Now you may notice that the surface area and the volume ended up being the same for the larger figure. I just made this problem up at random, so I don't know if that's even technically possible. It's just kind of happenstance. That doesn't usually happen. So that concludes our discussion of areas and volumes of similar solids.